So let's look at the circuit representation of a three-phase system. When you are solving a three-phase system, when you're trying to find different quantities, voltages, currents, power, in general, we solve stuff for a single phase. And specifically when our system is a balanced system. What is a balanced system? A balanced system is the one in which you have the same amount of load on each phase. For example, if you look here, this is a balanced system because you have R, the same resistance on each phase. So when you have a balanced system, generally we analyze a single phase of a system for the power, for the anything, voltage, current, and then we extend those for rest of the phases, and that's how we analyze the three-phase system. Now, three-phase systems are represented with different representations. The one very common representation, as we will see, the three-phase four-wire system, but we will start with three-phase six-wire system. So as we saw in the generator, three-phase generator, you have a loop of wire for each phase, and that's how this circuit is being drawn. So you have the phase A, current is going towards the load, and then return wire current is coming back to the coil, basically, in which the voltage is induced. Likewise, you have phase B, current is going towards the load and then coming back to the induced coil, and phase C like this, right? So this is a three-phase six-wire system, not very commonly used. Since the wire in which your current is returning is a single wire or a conductor which can carry all three current, instead of using multiple return wires, we use a single return wire and we call it neutral. And we have a three-phase four-wire system like this. So the current is going to come out of phase A, go through the load, and then come back. So that's going to be your current A. Likewise, current C, phase C current is going to go in this direction and go through the same wire. That's your IC. And likewise, IB is going to go like this, and the same wire IB. So through the neutral wire, you have all three currents are flowing, IA plus IB plus IC. Now for a balanced system, if you do the derivation of what will be the sum of all three currents, IA plus IB plus IC, which we are calling I neutral, then IA is VAN over R, VBN over R is IB, and VCN over R is IC. VAN over R, we taking VAN V peak, VBN is V peak angle negative 120 degrees. Again, this is phasor domain. We are dealing with the AC voltage, AC current, so we are not discussing in the time domain, we are discussing in phasor domain. Of course, we can always go from phasor domain to time domain. Our frequency is pretty much standard 60 Hertz or 50 Hertz. And then VCN is VP over angle negative 240 or positive 120. So when you solve this, basically go from the polar form of the complex number to the rectangular form and add all of those together, you're gonna see that for a balanced load, when all of them are R, you're gonna get a 0. That means for a balanced load, neutral is not carrying any current. And for a balanced load, that means we can remove the neutral wire since there is no current in the neutral wire. So we can have a three-phase, three-wire system. Of course, the system is not really implemented in practice. The one that is implemented is three-phase, four-wire system, where you do have a neutral wire, you have three phases, and of course you have ground included in the power system. So these are different representations of the circuit. This type of arrangement is called a Y arrangement of load. So the power, three-phase power, is always generated such that the coils are in Y arrangement. And if the load is also connected in the same configuration, then the load is connected to be in Y as well. What is Y? Basically Y is, and again I'm going to go to the three-phase four-wire system, which is easier to understand. A Y connection is such that the load is connected between the phase and the neutral. Like all these three loads, as you can see, are connected between phase, whichever phase they are connected to, B, C or A, and the neutral. So anytime phase is load is connected between the phase and neutral, that orientation is called a Y orientation. Now you can also have load connected between the two lines, that is between line A and line C, let's say. Now this type of orientation, as you will see shortly, is called delta orientation, or the load will be connected in delta. Now the source will never be connected in delta, it will always be a Y source, but load can be connected in either a Y, which is this, or delta, which is something like this. Makes a delta, that's why it's called delta load. And then between each of these, so it will be connected like this, A and B, like this. So this load R will be connected between line A and line B instead of line A and neutral, right? And likewise this can be connected to line C. So this load R will be connected between line A and line C instead of, again, line C and neutral. And this load R can be connected between line B and line C instead of, again, B and neutral or C and neutral. So this is called the delta configuration. And what is the property of delta configuration? That it is connected between the two lines. Instead of line and neutral, it is connected between line and line. So we have two different types of configuration. We have line and neutral and line and line. Line and neutral is also called phase voltage. Anything connected between line and neutral is said to be connected between it's said to be connected to a phase. Basically, it's called phase voltage. And any load which will be, of course, delta connected load connected between line and line, between two lines, is in general, in short, it is connected to a line. So that's the short form of that. Line and neutral, we call it phase, and line, we call it line in three phase. That is, if it's a single phase, of course, it's just gonna be the same. Line and phase is gonna be the same. But in three phase, if I give you the phase voltage is this, that means the voltage between line and neutral is this. If I give you line voltage is this, then that's gonna be between one line to the other line, the voltage is that. Okay, so as I said, you have delta connected load between two lines and Y connected load between line and neutral. So let's go ahead and look at what is the relationship between line and neutral and line voltage. So let's just take an example of line A and B. So the voltage between lines A and B. So if I go back from this line to this line, let me just draw this as getting messy. So if you have three phases, these three phases, let's say this is your neutral, your A, your B, your C. So this voltage is EAB between A and B. So EAB is equal to EAN. EAN is this minus EBN. EBN is this, right? So that's going to be EA to B, EAN minus EBN. So now you can again go and you know that EAN is the peak value of voltage, that's the magnitude of that, and angle is 0 degrees. EBN, the magnitude is the peak value, EP we are calling, and the phase is negative 120 degrees. Again, you convert this into rectangular form, and then you solve it, and you're gonna get this result right here. And when you convert this back into polar form, you're gonna get 1.732 E peak angle 30 degrees, or the magnitude of line to line voltage EAB is, magnitude of EAB is square root of 3 times the peak value of the voltage, and the phase of EAB is 30 degrees, right? Now you can also go ahead and find similarly EBC and ECA similar way, and you're gonna see that the magnitude of each of the line voltage is exactly the same. That is the square root of 3 times the peak value of the voltage, and the phase is going to be different. The phase will be 120 degrees apart from each other. So this is 30 degrees, this is 150 degrees, and then ECA is going to be right here, right? Oh, ECA is 150 degrees and EBC is negative 90 degrees, and magnitude is the same right here. So line to line voltages magnitude is same, like line to neutral voltages magnitude is same. Line to neutral voltage magnitude is what? E peak. Line to line magnitude is square root of 3 times E peak. So magnitude of line to line voltage is equal to square root of 3 times magnitude of line to neutral voltage. That's a standard result. And the phase of line to line voltage, again, they are 90 degrees apart from 120 degrees apart from each other, and they are leading the corresponding line to neutral voltage by 30 degrees. So if you look here, this is your line to neutral voltages, VAN, VBN, and VCN. So VAB or EAB is this, magnitude is square root of 3 times the line to neutral voltage, and angle is 30 degrees, right? This is EB, this is VBN or EBN, and this is your VBC. So it is leading the line to neutral voltage by 30 degrees, and the magnitude is square root of 3 times the magnitude of VBN. And likewise, this is your ECA, and this is your ECN. Sorry, this is your where is it? Oh, this is your ECN, sorry. This is your ECN, 120 degrees, and it is being, the ECA is leading ECN by 30 degrees, and the magnitude is square root of 3 times the peak value of line to neutral voltage. So remember this result. For line to line voltage, magnitude is square root of 3 times line to neutral voltage. Example 8.2, you can go through the examples, pretty straightforward example, you will understand it. And as I was mentioning, the connections, let's look at the delta connection real quick. In delta connection, as I said, load is connected between line to line. So observe, you have this line and you have this line, and you have Z delta, this Z delta connected between A and B. Likewise, you have Z delta, this is balanced load, connected between A and C, line C and line A, and Z delta this connected between line B and line C. So this is a delta connected load. Again, delta connected load, it will always be connected between line to line. Anytime a question is given to you that and it is mentioned load is delta connected, the first thing you're gonna do when you're drawing the circuit diagram is show the load connected between line to line. No, you don't have to show the whole the three-phase circuit. All you have to show is the delta connected load like this, and then C or A, B, C. So you can show 3 lines coming in, and this is your EAB, your voltage here, this is your ECA, the voltage here, and this is your EBC, the voltage here. Now here you have, this is the load current in each phase, and then you have the line current. Now in the Y connected load, line current and load current is the same, right? Line current and load current is the same. Here it is going to be different. As you can see in this circuit diagram, IA is the line current, IB is the line current, IC is the line current. But when it goes here, since this is a node, you have 2 currents over here. These are the load currents, IAB going into the load connected between A and B, ICA load connected between C and A, and then IBC load connected between B and C. These are load currents. So as you can see at this node, if I want to write down the equation, KCL equation, IA is going towards the node and ICA is going towards the node. So IA plus ICA will be equal to IAB, right? So we will discuss right over here. So when you solve this, IA is IAB minus ICA. IAB is EAB over Z, if the load is Z, minus ECA over Z. And EAB and ECE, we just figured out line to line voltage. EAB is square root of 3 times E peak, angle 30. ECA is square root of 3 times E peak, angle 150 degrees. So I converted those angles into corresponding rectangular form, or the polar number into corresponding rectangular form. And then what we get 3 E peak over Z. Now we can write 3 E peak as square root of 3 times square root of 3 E peak over Z. And then square root of 3 E peak is E line to line magnitude, right? So we put E line to line, and then E line to line over Z is the load current. As you can see, using Ohm's law, the line to line voltage, this line to line voltage divided by the impedance magnitude, or the impedance, is the load current. So the magnitude of the load, the line current, is square root of 3 times I load. Square root of 3 times I load. And the angle over here is 0. I'm not showing you, but the angle here is 0 because, of course, remember, IA is a complex quantity. And likewise, when you calculate IB and IC load current, line current, sorry, IB will be square root of 3 times I load, angle negative 120 degrees, and IC will be square root of 3 times I load, angle 120 degrees. So again, these line currents are complex quantities. They are 120 degrees apart from each other. The most important result that you need to remember for most of the problems, there are 2 things you need to remember. You need to remember that in delta connected load, I line, magnitude of I line, is equal to square root of 3 times I load for delta connected load. And for and then the line to line voltage, E line to line, is equal to square root of 3 times E line to neutral. So these are pretty much a standard result. Magnitude of the line current is equal to square root of 3 times magnitude of the load current in delta connected load. In Y connected load is the same. Line current and load current is the same. And line to line voltage magnitude is square root of 3 times line to neutral voltage magnitude. So keep that in mind. Do the examples. I'm showing you the examples. Do the examples. And since this is the last topic, I'm just going to cover it. Power transmitted in a 3-phase load is basically 3 times the power transmitted in a single phase load. You can, since it's a AC power that we are discussing, so like we discussed in the last chapter, you can have active power, reactive power, apparent power, complex power, and each type of power, once you analyze a single phase circuit, whatever power, if it's a balanced load again, whatever power you're getting from the single phase circuit, you could just multiply that by 3, and that's going to be the power for the whole 3-phase system. Look at different examples that I have put here. Example 8.4, example 8.5, and 8.6, for which circuit is given. The circuit is basically, the load is delta, this capacitor is delta connected. You have a motor which is Y connected motor, and the capacitor delta connected capacitor. So it's a very good example actually to show you how the 2 loads are connected with the same line. Remember, anything that is connected to the same line becomes parallel, right? So in this case, this is a 3-phase system. So what we are saying is you have a Y connected load connected between line and the neutral, and then you have the delta connected capacitor bank. This is the motor, this is the capacitor bank to correct the power factor of the line. So the capacitor bank is connected between the 2 lines, AB, AC, and BC. I could not draw the actual delta and actual Y, so but it's the same thing. Depends where exactly it is connected, that will make it Y or that will make it delta. So go over that example, and I also have another example right here. Three-phase balanced load comprised of three impedances connected to 60 Hz 220 volt system. Now in this case we are also considering line reactance and line resistance. What is line reactance and line resistance? Basically, when the power line is coming and connecting to the load, that power line has some inductance which is more than the resistance of the line. So that's what we are showing here. Now remember, anytime you have inductive reactance, it's not going to be given as J10 ohm. In generally it will be just given as over here 10 ohm inductive reactance. So make sure you put J by yourself because it's a complex quantity, right? Inductor, capacitor, and resistor is not a complex quantity, but inductive reactance is, and capacitive reactance is. Okay, so the phase per line is 100 angle 30 degrees. So what we're gonna do, we're gonna evaluate the single phase out of the three phases, and if it is not given to you how the load is connected, delta or Y, always assume it's connected in Y if it is not given. So we will evaluate a single phase, and then we extend our results for the rest of the two phases. So we evaluated everything, simple series circuit. We evaluated what is the load power per phase, reactive load power per phase, and then we multiply each by 3 to say, okay, this is the total power of the system. So go over the example, do these examples, don't just read the examples, make sure you do these examples to get more practice. And then the next thing are problems that I have assigned you, and hopefully you will be able to do the problems. In the problems I will mention one thing. There's a problem right here which I'm asking you, that circuit diagram is going to help right here. Now in this problem, basically the arrangement is that you have three loads connected in delta, right? And you have lines A, B, and C, and then I'm asking you that for some reason one of the line fuse burns out, so that means that this line is gone, let's say right here. So how the loads are connected now? This load Z is connected between A and B, and now you have two more loads, these two Z's, which will appear in series between A and B. So the current is going to enter here, and since this line is burned out, it cannot go here, it's gonna come here, right? So this is the arrangement. You have one load connected between line A and B, and these two loads also connected between line A and B. So what's going on here? You have two loads in parallel. One is Z and one is a series combination of two Z's, right? So this is how you're going to solve this circuit, and you're going to figure out what is the total power supply. Just wanted to clarify this thing. I hope you will do the problems, and hope you will not have any trouble doing this problem. There are more than enough examples that I have put. Do the examples again, don't just read the example, do the examples, get some more practice, and then do the problem.